So today I'll be presenting you a few-shot learning approach using Siamese networks for interpretable software defects prediction. Now, what is defect prediction? It's the process of identifying software modules that are likely to be faulty in the future, or in next releases, to say so. It is a vital activity across all stages of the software lifecycle because it enables targeted testing and code review, thereby improving software quality and reliability. It's important because by predicting which part of the software is most likely to be defective, organizations can allocate resources more effectively, reduce maintenance costs, and prevent costly errors from reaching production. We have a few challenges in this field, first of which is the severe class imbalance, because defective modules tend to happen less likely than non-defective ones. And then we have the data scarcity, because in many real-life scenarios, defects are not labeled as soon as possible or at all, especially for new or evolving software. And then we have the feature selection problem, because the quality of the training data should be improved by determining relevant features that are highly correlated with the error proneness of a piece of code. Traditional approaches in the field use supervised machine learning, evolutionary computation, fuzzy logic, and deep learning models. However, many struggle with the class imbalance and require large labeled datasets. Few-shot learning approaches or one-shot learning approaches, especially with using Siamese neural networks, have recently been explored to address these limitations, but prior models have typically been shallow and evaluated on small and outdated datasets. A way of addressing this issue is by applying the few-shot learning paradigm, where the focus is on obtaining accurate prediction, even if the training data is scarce. Few-shot learning is used mainly in image classification and addresses machine learning models that learn to estimate similarity of two instances, or the probability that they belong to the same class, using a relatively small training dataset. Unlike a classical deep learning model, these models need little training data or just even an example of each class may be enough, but the prediction requires both the training model and the training dataset, because the model learns to differentiate between the input image and the images from the training set. Now, Siamese neural networks can be used to create few-shot learning models. Their architecture consists of two networks that are identical and receive distinct inputs and are joined at the bottom by a function that computes the distance between these two entries. Based on this distance, the model decides where the two inputs are of the same class or not. These are the research questions that we will address. We want to know how to design a few-shot learning approach using Siamese neural networks. To what extent does the feature-based representation of the data influences the model's performance, and how is it compared to similar work? And then finally, how can we discover by applying explainability? What can we discover by applying explainability to our model classifier? As a case study, we used Apache Calcite, which is an open source data management framework. It includes 16 releases, and for each one, the datasets contain the application classes from the releases, represented as a real valued vector, plus one binary label indicating if the class was identified as being defective or not. The features used to represent the application classes are software metrics, including static code software metrics, warnings produced by analysis tools, and so on. An analysis of the dataset revealed that over 900 software metrics were zero valued, and we excluded those from the initial dataset. Another observation is that the non-defective entities significantly outnumber the defective ones. This table reveals a severe data imbalance that increases with the software evolution. We note a general decreasing tendency for the number of defects during software development, which results in a very strong correlation between the size of the software and defective rate. We answer research question number 1 by introducing the methodology applied in our few-shot learning-based approach, using Siamese Neural Networks to predict software defects. The main motivation behind proposing this model was to try to overcome the severe class imbalance of the training datasets. The architecture of our model is detailed in this figure. The input of the model is a pair of 2 instances. The goal is to encode both instances using the same network, compare the encodings, and then make a prediction based on that encoding. Basically predict if the instances belong to the same class or not. To encode each instance, we use 2 Siamese neural networks that have the same architecture and weights. Each network is compared of 26 dense hidden layers plus 1 dropout. The encodings of the 2 instances are then compared using an absolute distance layer, which then passes the output to a dense layer, which will basically provide the final prediction. The objective is to predict defects for version X, where the training data are the first X-1 releases. In terms of data preprocessing, we extracted randomly a subset of non-defects to rebalance the number of defects to non-defects and reduce the model's bias. Then the data is split into validation and training sets, and the model is fed pair of instances containing at least 1 positive instance to further emphasize the recognition of defects. To further optimize the training process and mitigate the risk of overfitting, an early stopping strategy was employed. Specifically, we decided to stop after 30 consecutive epochs, no improvement was done. For classifying an instance C from the testing dataset, it is paired with all instances from the preprocessed training dataset, and all these pairs are then sent to the network. Thus, estimated similarities between the given instance and each instance of the training set are provided. Based on these similarities, we are computing a positive and negative score, and then the classification of C is the class with the highest score, basically. For evaluating the performance of the model on a specific testing dataset, the confusion matrix is computed considering the defective class as a positive and the non-defective class as a negative. Based on these values from the confusion matrix, the following metrics are calculated. Our focus will be on MCC, as it is employed in the machine learning literature for imbalance classification, CSI, which is used primarily in forecasting rare events, and AUC, which is considered state-of-the-art evaluation metric for this problem. Okay, now this table illustrates the results obtained after training on the selected subset of the best 2,500 features. Overall, the model maintains a high recall, which means that it is efficient in identifying most of the defective classes. And this is important because failing to detect a defective component can be more critical than misclassifying a non-defective one. However, this comes with the cost of a lower precision, resulting in relatively high number of false positives, this being known as a challenge when working with imbalanced datasets. As the software evolves, the number of classes increases steadily, while the proportion of defective classes decreases significantly. This is considered a common software engineering observation, where mature systems tend to have fewer defects, directly impacting the predicting difficulty. For example, in version 1.15.0, although the model achieved a perfect recall with 0 false negatives, the precision drops to 15.8%, reflecting a large number of false positives and lowering the values of F1 score and MCC. In contrast, if we look at the experiments on version 1.10.0, we can observe a moderate defect rate. We can see that there is the highest MCC and F1 scores, suggesting an optimal balance between the number of defects and the precision of the model. Overall, the AUC value remains relatively high, indicating a consistent separation capability of the model. Given the high recall and specificity values, the AUC value confirms that the model successfully balances sensitivity and specificity as the class distributions becomes increasingly skewed. Now, I mentioned previously that the table was showing us results for the top 2,500 features. As a pre-processing kind of step, we decided to, or not pre-processing, but we decided to perform experiments first on all of the features and then apply univariate feature selection to kind of understand and select the best features that mostly correlate with the basically what we are interested in, whether the instance is defective or not. So to put it into perspective, after applying univariate feature selection, the precision was improved by 16%. The model's ability to distinguish between classes benefited, meaning that AUC increased by 2.5%. AUC PRC improved by 6.6%. And in addition, the false positive rate decreased by 24% and the false negative rate rose slightly, reflecting a trade-off in favor of detecting more defects. To further understand the results of our model, we have turned to machine learning explainability techniques, namely LIME. This is a technique meant to help understand what are the relevant features for a classifier when it classifies a certain instance. The results of the LIME analysis of an instance is a list of weights, one weight for each feature of the given instance. The weight signs indicate in the class for which the feature contributes. So positive for defects, negative for non-defects. Here in this image, we consider two non-defective application classes from release 1.10.0, because that's the one that performed the best, that were misclassified by our model, so were classified as defects, although they were non-defects. We note that even if more than 10 software metrics contribute to the classification of the instance as belonging to the non-defective class, their contribution is relatively low, as the instance is still predicted as a defect. This suggests that while the model can correctly label these instances, it often does so based on weak weights. As a result, the representation of non-defective classes through software metrics may not be particularly distinctive, perhaps contributing to the high rate of false positives observed in our experiments. These findings highlight the need for further investigation into the quality and relevance of the feature space used in the training process. In this table, we compare our findings with the three most recent studies that used the Calcite dataset. The first two entries represent the performance of two one-class SVM models. The first one is trained on defective classes, and the second one is trained on non-defective classes. And then finally, we have a support vector machine, which is a binary classificator. The experiments performed on these models were carried out cross-version, so in the same way as in our work, allowing us for a direct comparison. We observed that while our model does not achieve the highest precision or specificity, it significantly outperforms all other models in recall, AUC, and AUC PRC. These metrics are crucial in imbalance classification tasks, where identifying as many true defects as possible is typically prioritized. The support vector machine models show strong performance in precision, specificity, and MCC, suggesting that it is highly conservative and less likely to produce false positives. However, its recall is substantially lower, meaning that it misses more defects. Overall, our model achieves a balanced performance across all metrics and demonstrates resilience to data imbalancement. We did not try to compare ourselves with other few-shot learning approaches because most of them base their findings on a NASA dataset, which is known to be outdated and problematic, with instances overlapping in the training and testing datasets, thus creating a performance inflation in models using it. In conclusion, we proposed a robust and interpretable model, which is effective for realistic defect prediction scenarios. It handles well cases of severe data imbalancement and scarcity. Now, if you have questions,